Hello there, this is the last lecture of week 6. We'll be done with logic coverage criteria with this lecture. Next week I'll begin with a new test case design algorithm. What are we going to do today? We're going to look at how logic coverage criteria applies to finite state machines. So this is the same slide that I've shown you in every lecture that we did in logic coverage criteria, meant to be as a recap of the various coverage criteria that we saw and their subsumption. In today's example, when we do finite state machines, we'll see maybe 2 or 3 of these coverage criteria and see how to write test requirements and test cases for those for specifications that come from finite state machines. So we introduced finite state machines when we did graph-based testing. They have nodes or vertices which are states, and the edges in finite state machines are called transitions. Edges are labeled with actions, events, and also guards, which are basically conditions that tell you that when an event can happen and when it happens, the resulting action can happen. Finite state machines have designated initial states. They may or may not have final states. They're very popular model for specifications, for design. They occur as UML state diagrams, especially in the embedded control software domain. Finite state machines are routinely used to specify control algorithms. So we'll see how to apply logic coverage criteria for finite state machines using an example. So here is an example of a very small finite state machine. In real life, finite state machines that correspond to realistic models hardly are so small, but what people do is what is called modular design. They come up with initially a very high level finite state machine that acts as a specification or as a design model. As and when they get clarity, they keep refining or adding details to their finite state machine. So even though it's a small machine here that we are looking at in this example, it has enough details, enough predicates for us to be able to look at how logic coverage criteria applies to this. So this is a machine of, let's say, a model of how the doors of a subway train runs. Subway train or a metro train. So these trains keep moving from one station to the other, and the way they move, they have doors. The trains have doors on both sides, and typically for safety reasons, if the platform on a particular station comes on the left side, then it's expected that only the doors on the left hand side open, the rows on the right hand side are closed. And if a particular station comes in such a way that there is platform accessible on both sides, then both sides doors open. And when the train is moving, which means it is inside a subway tunnel, then you expect both the doors to be closed. So here is a state machine of a subway train that has 4 states that talk about what are the status of all the doors in the train. So the initial state is this state which says all the doors of the train are closed. From that state, it could move to one of these 2 states. It could either move to a state where all the left doors are open, or it could move to a state where all the right doors are open. And from either of these states, left doors open or all right doors open, it could move to a state which says all the doors are open. So each of these moves or transitions are guarded by a whole set of conditions, as you can see here. For example, from the state all doors closed to the state left doors open, if I have to take that transition, then all these conditions must be true. The finite state machine has access to all these variables. Like in program, you see the variables right in the beginning. Finite state machines, they are not explicitly declared, but we assume that eventually this finite state machine design or specification is meant to be modeled, implemented using code. So all these will surface as real variables that will be in the code corresponding to the finite state machine. So there is a variable that talks about the speed of a train called train speed. It says that train speed should be 0, which means the train should not be moving. There is a variable which says where is the platform? Is the platform on the left hand side or is the platform on the right hand side? So in this case, the guard to transition to left doors open, the platform should be on the left hand side. And there is another variable which talks about the location of the station, location of the train. It says the train is in station, which means it's come inside the station, and it's either this or there is an emergency stop. Somebody's pressed the emergency stop button, and because there's an emergency stop, somebody is trying to open the door by overriding it while the train is still in the tunnel. But the train is not moving in all the cases. So there are so many variables, and this large guard tells you when the transition from all doors closed to left doors open happens. So it says train should not be moving, platform should be in the station, and the platform should be on the left side, and the train should be in station. Either this, or there was an emergency stop, somebody is trying to override open the doors, and the train is still in the tunnel. So now similarly, from the state all doors closed to the state right doors open, when do I go? Again, the train should not be moving, platform should be on the right, location should be in station. I'm sorry, this has gone out of the slide a little bit. Emergency stop, override open, location in tunnel. It's an exact replica of this. The only condition that has changed is that the platform has come on the right hand side for this transition. Now it so happens that the second platform is on the right hand side, and there is a platform on the right hand side. Then apart from the left doors, you can open the right doors implicitly, and you go to a state which says all doors are open. And similarly, if there is a second when the right doors are open, if there is a second platform on the left hand side, then you could open the left doors also and go to a state all doors open. And from the state all doors open to the state all doors closed, how do we go? We go when the doors are clear and somebody presses the close door button, and there is no emergency stop and nobody has pressed override open. So is it clear how this simple state machine looks like? And why have I drawn it this way? We've drawn it this way because the focus of this lecture is to be able to illustrate the use of logical predicates as they come in finite state machines. So this state machine, even at this level, could have actions. We have not really specified all that because I want to be able to focus on logical predicate. So if you see, there are so many predicates that we can consider, 5 of them here. Just for illustrative purposes, let me take this predicate, the one on the bottom left, which lets you go from the state all doors closed to the state left doors open. We'll take this predicate and illustrate the use of logic coverage criteria that we learned on testing this predicate, indirectly testing the influence of that predicate or guard on the finite state machine. So I have just written the predicate that I want to consider. So this is the predicate. It says train speed 0, platform is on the left, the train is in station, or somebody's pressed the emergency stop, doing override open while the train is still in the tunnel. This occurs as a guard in the transition from the state of all doors being closed to the state of left doors being open. How many clauses does this predicate have? Let's count. This is 1, train speed equal to 0, platform equal to left is the second clause, location in station is the third clause, emergency stop fourth one, override open fifth clause, location is equal to in tunnel sixth clause. Predicate coverage criteria for this predicate is very easy. It will tell you basically whether you can take this transition or not. You can take this transition if this predicate is true, which means if the clauses that are connected by an AND are true, otherwise you cannot take the transition. So that's what predicate coverage criteria will say. Now we'll work out active clause coverage criteria for this predicate. So I take this predicate. It has 6 clauses. What is the first step to do to determine active clause coverage criteria? Per clause, I have to say, call it as a major clause and see when that clause determines the predicate. So if A is one of the clauses in the predicate, I do what is called determining P subscript A. So I have worked it out offline. I seriously urge you to take this predicate and work out for each of the 6 clauses when that clause will determine the predicate, using the formula that says replace the clause with true in the predicate, replace the clause with false in the predicate, and XOR them. That's the formula if you remember. So I use that formula, I have worked it out, and for the first clause in the predicate, which is train speed is equal to 0, after simplification, this is the PA value. That is, this is the P train speed is equal to 0 value. And similarly, I have also worked out for the clause override open, after doing the same formula, substituting override open with true ones, substituting override open with false one, and XORing them and simplifying the resulting formula, I will get this simplified predicate. Similarly, for all the remaining 4 clauses, we can compute, if that clause is the major clause, the conditions under which that clause will determine the predicate. I have just done 2 of them here. The remaining 4 can be worked out. In fact, for these 2 also, I have given you the final resulting formula. I have not given you the steps of working. So we take the first one, which is train speed 0, and the other one that we've worked out, which is override open. And remember, what are these? This is like a formula in conjunctive, disjunctive, normal form that we saw in the last lecture. So it's very easy to write ACC test requirements for these formulas. What do? You make all the other clauses take value true, and the clause that is your major clause, make it true once, make it false once. Similarly, whenever override open is a major clause, you make it true once, you make it false once. The rest of the clauses are all made true, provided the diagonal, along the diagonal. It so happens that override open is the 4th clause in this predicate. 1, 2, 3, 4, 5th clause. Sorry, it's the 5th clause in this predicate. So the diagonal corresponding to that will be false. The rest of the values will all be true. So this is how you write correlated active clause coverage criteria, TR, for that. I have just given you for the 2 clauses for which we worked out here and gave when that clause determines the predicate. There are 4 more clauses. After you work them out, you can fill up this table and see how it looks like. So this is the TR for CACC for the predicate. So to be able to give test cases for this TR, you have to make train speed value 0. You should ensure that the platform is set to left. In station as a Boolean variable should be made true. Emergency stop should be made true. Override open should be made true. And in tunnel should be made true. This is how a test case for that will look like. So now you'll realize that there is problem here. If you think a little bit about it, in this example itself, we do have a bit of a problem. If you see, for train speed 0 to be the major clause and for it to be influencing the predicate, look at the test case for that. Each of these values should be made. Now, if you see, is it actually feasible to make each of them true in the realistic scenario that the finite state machine would be implemented in? It will not. Why is that so? Because if you see, it says in station is set to true and in tunnel is also set to true in both these cases, which means that the train is in station and in the tunnel at the same time. That is not practically possible, right? It is either in the station or in the tunnel. So there could be a possible error, or you could interpret it as that the finite state machine that we saw at its level of abstraction doesn't give enough details to be able to specify what we need. In fact, you could find several other errors. Here is one more. Suppose I try to write a CACC TR test requirement for another clause in station, which is here, which is one of the clauses that come in the predicate. So here again, you will realize that if this is the major clause, I make it true once, false once. The rest of it take true, false values. If you see, what I have done here is it says in station is false here and in station is false here, which means it says the reverse of what the previous thing said. It says that the train is neither in station nor in tunnel. It's just disappeared. That also is wrong, right? There's something incomplete in the specification. This one said the train is both in the station and in the tunnel. Not clear. This says the train is neither not in the station and not in the tunnel. It's the second row here. If you see, both are marked false. That's also not possible. So it could be interpreted as two things. You could say that in this finite state machine model, I have found 2 errors. There is inconsistency in specifying exactly where will the train be. The predicates or guards don't really factor in the consideration that the train can be in either in station or in tunnel. So these guards are not clearly specified, and that there is an error in the finite state machine. Or another way to be treated it as is to say that there is incomplete. This is incomplete because the way it specifies, it doesn't give details about train being in exactly one of the locations. So more details have to be added, or that the finite state machine has to be refined to be able to complete that. Either way, whatever it is, we have found a possible bug in the model, and logic coverage criteria are very useful to be able to do this. So similarly, if you work out for the other remaining clauses, you could find more inconsistencies and more errors. I just did 2 because in this particular case, just these 2 were good enough to find inconsistencies or potential errors in the finite state machine as a specification. But there could be a couple of other issues also. Now, when you're looking at in code, like when we saw logic coverage criteria as it applies to code, when we saw the 2 examples, the thermostat and the triangle type, we told you that if a particular logic coverage criteria has internal variables, how to solve it for them, how to ensure reachability. But when we apply logic coverage criteria for finite state machines, as I told you when I introduced you this example, there is no explicit notion of inputs and outputs. So what is a test case? Test case is directly given in terms of inputs and outputs that the finite state machine looks like, and outputs could also be given in terms of which is the resulting state. Sometimes there could be things wrong in the state that the Turing machine goes into, even though a state is not an explicit variable that occurs as a guard. So it's up to the tester to infer all these information from informal specifications of finite state machines or semi-formal specifications of finite state machines and complete the test case to identify a potential error or fault in the specification. They have to be explicitly derived. You cannot expect them to be present and readily available as they are with code. So usually testing based on finite state machines is a very popular testing. There are huge number of papers that are in this area, broadly called as model-based testing. It helps in early detection of errors. Why so? Because finite state machines typically are models of specification and design. Specification and design are done before we write code. So I have found a potential error right there before I write code. Instead of finding it much later after I write code, it helps in early detection of errors. If I detect it early rather than detecting it late, I save myself a lot of trouble with rework. So it saves a lot of cost and a lot of time. And you can check out the testing literature for a huge amount of material related to test case design on finite state machines. We've just covered logic-based testing. So this brings us to an end of logic-based testing. There will be an assignment this week that will deal with logic-based testing for code, specifications, and finite state machines. I'll try and upload a video next week that will let you tell you how to solve that assignment, but feel free to do it before you see the video. Thank you.